Welcome students to the first in a series of lectures about the chemistry chapter, which is chapter 2 in our book. As you can see from our little opening chart here, chemistry chapter is split into two parts. Part 1 is the basic chemistry, atoms, molecules, kind of the general chemistry type stuff. Part 2 is the biochemistry, focusing more specifically on the types of chemistry that goes on in the body. Before we dive into the meat of this chapter, first maybe let's watch a little video about why we are studying chemistry here at the start of an A&P class.
At this very moment, there are thousands of chemicals moving through your body, and the reaction of these chemicals are involved in every single physiological process. Since your goal as a healthcare professional is to help your patients maintain a healthy body, it's important to understand the chemistry that enables the body to function. For example, in the emergency room, we treat many patients experiencing dehydration, fluid loss, and electrolyte imbalances. In order to know which IV fluids need to be infused into patients suffering from these disorders, you need to understand the chemical effects that the fluids will have on the patient. When patients are dehydrated, it is important to replace their lost body fluids with solutions such as lactated ringers or normal saline. These solutions are used because of their sodium concentration. Water follows sodium in and out of cells, and getting the right calculation of sodium into the body is critical in rehydrating patients. By having a solid understanding of basic chemistry and biochemistry of the body, you'll be able to help your patients recover from dehydration, fluid loss, and other homeostatic imbalances.
So these little Why This Matters videos are in every chapter. I find them very useful. It gives you a little insight on how we're going to use and how you could potentially use this knowledge that you're going to gain in this class to help you further in your career. So let's dive into some general chemistry. Before we talk about energy, let's just talk about matter in general for a second. Matter, of course, is the stuff of the universe. It's the stuff that we are made of. It's the stardust, right, that we are all made of at some point. That's different from energy, which is, as it says on the screen there, the capacity to do work. Putting matter into motion, doing something with it. And so energy is a little different than matter, but they are both kind of fundamental principles of the universe. We have two types of energy. We have kinetic energy and potential energy. Kinetic energy is the energy of movement, the energy of action, whereas potential energy is what we call inactive or stored energy. And for the body, that mostly means chemical energy, the energy that is between the bonds of all of the different molecules inside our body. One of the first laws of thermodynamics, energy can be neither created nor destroyed, but it can be transformed from one type to another. We can take the potential energy, the chemical energy found in the bonds between our foods, break them apart, which releases energy, and then do something with that energy. So we go from potential to kinetic energy. Let's watch a video about those two things.
Energy is the capacity to perform work. Potential energy is energy that is stored. Kinetic energy is the energy of motion. Energy is neither created nor destroyed, but converted from one form to another. This property is called the conservation of energy. The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
So that's a nice little kind of summary of the energy transfer that goes on in our body. I've got a nice little diagram of that in just a second. But before we get to that little diagram, let's talk about the different types of energy that we might find. You saw there chemical energy. It's what we see stored in the bonds between all our molecules. There's chemical energy in our food. There's chemical energy in our bodies in the form of ATP. Electrical energy we have in our body as well. It's the movement of charged particles. We have particles and ions inside our bodies that are charged. So we have electrical currents. Our nervous system is mostly electrical energy. Mechanical energy is the actual energy involved in moving things. So water flowing down a hill, powering a water wheel, that's all mechanical energy. When we have, for instance, here, this lightning. This is electrical energy, charged particles. And then we have things like electromagnetic energy. I'm sure you've heard of the electromagnetic spectrum before. Heat, our most disordered energy form, is electromagnetic. Visible light allows us to see, and then things like UV from the sun and X-rays. So when you go and get an X-ray because you broke a bone, that is all different forms of radiant or electromagnetic energy. So there are lots of different types of energy that we see in the body and that we make use of in the body, including things like electromagnetic energy. So let's look at those energy conversions more specifically here in the body. So here we go. We're ingesting food. We're getting some chemical energy in our food. Some of that we're going to put right away into growth. Some of it we can't use at all, and so we just get rid of some of it through our feces. What we absorb in terms of our energy that we get from our food, we can use to do work in our body. We can make new things, which is biosynthesis. We can just kind of maintain what levels we're at, kind of a maintenance type function. And then we can do external work. We can walk and talk and run and play and so on and so forth. And you can see all of these kind of conversions between the food energy and the ATP energy to do biosynthesis, and all of this is not 100% efficient. Although our bodies are amazing in what they can do, energy conversions are not 100% efficient, although we're a whole lot more efficient about that than most computers. And so we do lose some of that as heat that we can't do any kind of useful work with. But some we can use for doing useful mechanical work. When you pick up a book, when you throw a ball, that's all mechanical energy. And some, again, we do lose because we just can't either absorb that type of chemical energy. Some stuff we can't absorb and we just lose it as feces. And then we do lose some because it becomes heat and unstable. Let's talk about atomic structure. So what we consider kind of our usual models, what we call the Bohr model, where we have the center nucleus and then this what we call an electron cloud that kind of roams and flows around the central nucleus. Inside the nucleus are our protons and our neutrons, and then around in the cloud are our electrons. Protons are positively charged, electrons are negatively charged, and neutrons, neutral, no charge. So right now you're just looking at a helium atom, which has 2 protons, 2 neutrons, and 2 electrons. You'll see that each atom has the same number of protons as it has electrons and vice versa. It's the neutrons that sometimes the number of them that can change. And the number of protons, the number of electrons is what determines what each element is. And if you change that, if you change the number of protons, you change the number of electrons, then you are changing one element into another element. But as I kind of mentioned, those neutrally charged subatomic particles are neutrons. They can change without changing the actual form and function of the element. And we call those isotopes. They're basically variations of a particular atom. They've got the same atomic number, but their mass numbers are different, the sum of their protons and their neutrons, because they differ in their number of neutrons. And so you're looking at here, this is our normal oxygen 16, but you can see oxygen also exists as oxygen 18, where it has 2 more neutrons than is typical. Isotopes can be stable or unstable. The stable isotopes are the ones that don't decay. So for instance, carbon-13 is heavier than carbon-12, but it's a stable form. It exists in nature without falling apart. Same thing with nitrogen-15 and nitrogen-14. Nitrogen-15 is the isotope of nitrogen-14, but both exist in a stable form in nature. What's really neat about stable isotopes is we can use them in wildlife ecology, in population studies. Our personal signatures come to reflect, particularly in things like carbon, nitrogen, sulfur, I think is another one that they use a lot. What we eat and where we live. And so we can look at a piece of skin tissue or the piece of a turtle's shell, which is what I did with my master's thesis, and actually look at their stable isotope profiles and determine where they lived or where they ate or and so on and so forth. And so we can track migration patterns and look at what trophic level, where kind of on the hierarchy of organisms a particular animal is eating, and so they're incredibly, incredibly useful for that kind of science. Conversely, radioisotopes we use a lot for diagnosis. If you're getting radiation for cancer, we can use it to treat cancer sometimes. Radioisotopes are what we call radioactive. They are not stable. They will spontaneously decay from the heavier element to the more stable form. So if we were to, instance, look at a hydrogen, hydrogen has 2 other isotopes. There's H2 and then H3. H3, which has 2 extra neutrons is much more unstable than H2, which only has one extra neutron. But the heavier the element is, the more unstable it becomes. And in fact, they can be so unstable that when they do decay, we get this little tiny explosion, as it were, and the element could actually become a different element because it loses so much of its nucleus. And the reason these things are unstable is due to something that we call quarks, which are subatomic particles. They're the little tiny particles that we find inside protons and neutrons and electrons. But then we're getting into quantum physics, and that is way above all of our pay grades. Molecules and compounds, right? So we talked about elements, so now let's talk about when we can get those elements and we put them together. If we have two or more atoms of the same kind, then we have a molecule or a compound. If we have two or more different kinds of elements bonded together, then we have a compound. So as you see here, glucose, C6H12O6, is a compound and a molecule, but hydrogen gas is only a molecule because it's the same kind of atoms. It's two hydrogen atoms, whereas glucose here has multiple different kinds of atoms, so that makes it a compound. Almost everything in our bodies especially, but most matter in general, exists as what we call a mixture, where the different components get physically mixed. There's no chemical bonding, we're not making or breaking anything. They can still be separated, but we're physically mixing these things. There are three types of mixtures: solutions, colloids, and suspensions. And the differences between those three is really all about particle size. In solutions, the particles are incredibly tiny, and so they spread kind of homogeneously throughout the solvent, the liquid. Colloids are things like, as you can see here, oil and water. They don't mix, right? That's a kind of a common thing. When you shake up your salad dressing, the oil will mix with the water, but if you let it sit, it kind of starts to settle out. And that's because in colloids, the particles are a little bit bigger, and so they kind of clump together, and they don't mix as well with the fluid. And then in suspensions, we have even larger particles. I always think of, in the body, we're talking about blood. Blood is definitely a suspension. If we go back, I think, in that slide. Whoop, wrong way. Yeah, there you go. If you were to, and you will actually in A&P II, centrifuge this blood, spin it out, all of the heavier stuff, all of the red blood cells and white blood cells will settle out to the bottom of this, leaving nothing but the fluid, the plasma, up here. And so suspensions have much larger particle sizes than colloids and solutions. And that's really kind of the difference between those three mixtures, which can be a little kind of confusing for some students. Now, if we were to look at mixtures versus compounds, compounds require chemical bonding. So we're actually, putting things together chemically. And if we wanted to separate them, we'd have to break those chemical bonds. So they're all compounds are homogeneous. They're completely kind of similar throughout. Conversely, mixtures, there's no chemical bonding, and they can be separated by physical means, like perhaps doing some centrifugation or straining or filtering. And so mixtures can be homogeneous, like a solution where it's kind of all spread out really evenly, or they can be heterogeneous, where they're not quite as evenly mixed. And that's really kind of the differences there. Alrighty, that is the end of part A of chapter 2.